only got 10 minutes, and I think we've definitely spent a lot more than that already talking about invalidations in the past. So all I'm hoping to share with you guys today is a bit of a fresh perspective, looking at it from another angle and saying, if we stop looking at type stability so much as an issue, what else can we find out about the invalidation problem, and how might we be able to tackle that? So first thing we should do is kind of start to hone in on this problem. One issue that can happen a lot that I think people have hit in the open source ecosystem is when you extend methods where you shouldn't. This frequently causes invalidations because no one else is extending that method. There's maybe just one generic definition in base, and then you provide the second one, and a large portion of the ecosystem invalidates. This can happen, for example, if you accidentally provide the one argument version of hash instead of the two argument version. Really subtle, but really important if you want to avoid these kind of latency problems. The issue that I want to focus on today is going to be the second issue here, which is when you're actually doing everything right. Like the author of the package said that you're doing the right thing. They wrote their code knowing that they might dispatch the method that you're providing. You're not committing type piracy, and yet we still got invalidations. So we're trying to kind of look at the happy scenario here where the user should be able to do everything they want, and yet somehow they have trouble having their cake and eating it too. So then we're going to be talking, in order to get to that, we're going to necessarily have to start looking at type unstable code. Type stable code is great. By no means, we've got nothing against it. That's awesome, but not every code can be type stable. And Julia makes it really easy to write type unstable code. It's one of our biggest kind of marketing pitches, so we want to make sure that this works well for users. And right now, the reality is you can easily end up invalidating, even if you're following all the rules, just if you have type unstable code. So yes, it's true that type stable code mostly doesn't have this problem, but today we're going to say, actually, you wrote type unstable code, and we want that to work for you as well as it possibly can. Where does this actual invalidation end up happening? Well, there's a whole pipeline of the compiler where we go from your source code to specializing this function and then evaluating a call that ends up invalidated at some point later. For what we're talking about today, we mostly don't need to worry about that pipeline. The key detail is that at some point we do something called call resolution, where we end up evaluating, in this case, a call to convert that knows you're passing in the specific type string, but what it doesn't know very well is the second argument, which is any type at all. And so the compiler here might look up the list of methods that match. And this is a pretty wide call. Any can match any type in the system at all. But in this case, we'll say that the compiler got lucky. I mean, this is totally fictitious here, but we'll say that it matched only two methods. And then everything else it knows would be a method error. So the idea here is that the compiler can compile those two methods, and then it can kind of speculate and say, man, I hope that this doesn't match anything else in the future. Boy, would that be great, because I've already got all the code you need. And if it's wrong, then you invalidate. And that's kind of where the root source of this problem here is, that you end up with wide calls in your code, and then we hope that the small list of methods we got back remains small in the future, and it doesn't. So let's look a little bit at that in more detail, especially as it applies to like multiple functions calling each other. So here you can see here that we start with one body of code calling another body of code, and that call starts out static. And then what happens is maybe someone else adds a new method here. So we had one match at first, but this is designed to be extended. So we have some wide signature like the one we were seeing before, and now we get a second method in that list. Okay, the compiler says, you know what, two methods, I can still manage with two methods. That's not too bad. So it adds a union split in your code. That's a fancy little optimization, but it basically means that we now have two dispatches, or two invokes of the static methods that we know might be there. And we say, great, let's hope that it's really just two now. You added one, that was already not great, we invalidated code. Let's hope we don't have to do it again. And then it does happen again, so now we get a full-blown dynamic dispatch. And we're like, oh, this sucks. I don't know anything about the type of any of these functions that they're returning. It's much slower than a normal invoke of this code. You know, a normal Julia developer, I think, would look at the code type and say, oh, this is not good, we shouldn't end up here. But I think if we zoom in to what happened here, we actually might conclude a little bit the opposite. So if you look at the life cycle of what happened here, remember we started from the assumption your call is going to be wide. It's going to have many callees. So in a way, we expect this scenario to happen with many callees. So we started from the scenario with just one callee, and we added one and we got an invalidation, and then we added a couple more, and we got more invalidations. And we got to this point at the end where we had the dynamic dispatch. And at the stage where we have the dynamic dispatch, your code is now the slowest it will ever be. In fact, invalidations only ever add a ton of JIT latency to slow down your code compared to what it used to be, but so that it can have new functionality in terms of being able to call new targets that it couldn't call before. So that's really interesting. It doesn't feel like a great position to be in, but it's actually exactly where we want it to be, because if we think about it here, you have many callees. We know that this code is going to be type unstable. So in a way, that dynamic dispatch was the right thing to do. In fact, if we go back to look at the code again, and look at these side by side, we said, oh, look, static dispatch to a single callee, that's great. That's a single invoke. That's great for performance, but it was actually the wrong code to emit because I knew you were going to end up with lots of callees later. And so in reality, that code was the code that we couldn't use at all. We pre-compiled it, and then it was useless. And the code that was useful was the quote-unquote bad code, which is this dynamic call to many callees. And so that's a very interesting perspective, is if you accept the type instability, then the problem is actually about understanding when you can eagerly say your method list is going to stop growing, or when you can say, actually, we expect this to be extended by people in the future. So for type unstable calls, we have to kind of guess about this. And if it guesses wrong, we get invalidations. So if that's kind of the premise here, that's the core speculation that's going wrong, then what can we do about it? You know, like if this is our perspective and this is the specific form of invalidation we're trying to fix, what can we do? I'm not sure. We're not going to tackle all the options here, but there is a couple I think I want to put in front of you, and a couple of options that I think people have talked about that may or may not solve this problem completely. One is that we could try to just disable world splitting. World splitting was that case where we have this really wide function call. We have a little bit of it matching on a couple specific types, but the majority of the call is totally uncovered and unimplemented. And in that case, sure, you could do that, and maybe for the convert code, we're okay with giving up some performance there. But I think that overall, this optimization is actually quite important for two reasons. One case is that it's very common to have functions that are really not extended at all. Internal functions in a package, for example, that you create for yourself, you just create a function, some internal function name. You maybe created your own little type hierarchy here with an abstract type and created your own types under it, but you never actually expect this to be used by someone else. So these methods are never going to get extended, which means that if the compiler is able to do what it can do today right now, where on the right-hand side it looks at that internal bar call, and it may not know very much about obj. All it knows about obj is that it's some abstract object, which sure, right now that's just type 1 and type 2, but later when we add other types, it could be all sorts of other things. So the compiler doesn't really know very much anything useful about obj. But what it can say is, I know that there are exactly 2 implementations of internal bar, and they both return string. So all of a sudden, out of something that was effectively super type unstable, basically any, we got back down to a really type stable return type, which is the string type here. And that's something that happens all the time in internal package code, and I don't think we want to just give up that optimization completely, because this would cause the reverse problem now, where we kind of assume everything might be extended, and in the frequent case where it isn't extended, we now pay a huge performance cost that doesn't give any benefit to the user. There's another problem here too, which is that it doesn't solve the unexpected specialization problem. This is a case where you have a call, like a call for show type, and this is technically covered by a generic implementation, like a default implementation provided by the package, or in this case, a default implementation in base. And then you might want to allow the user to override that. Sometimes that's very intentional. Sometimes the generic implementation is just an error that says, hey, you're supposed to implement this. And so we want to also be able to allow generic implementations to be overridable, but maybe not all of the time. I think show type is a case where we may not want to allow this to be overrided, but a lot of users do want that, and I think our ambiguity about, is this allowed and the compiler is going to expect you to do it, or is it not allowed and you shouldn't be overriding this generic implementation, that ambiguity is something we pay for a lot in the form of invalidations. And I think there are definitely lots of cases in the ecosystem where we do want to support this kind of overriding. So for that reason, also, I don't think that disabling world splitting alone is enough to solve this problem, because we do see this a lot in other packages. The other solution here, I mean, very hand-wavy, but we could just try to cache more aggressively. However, my response to this is really just a general level of compiler skepticism. I think that like a lot of the experiences we like to provide for the users are inherently dynamic with brand new code. We've got revise working, we have REPL working, and we can try to save a lot of the effort that your compiler does, but sometimes your compiler just does brand new work. And it's definitely a huge additional cost if a significant fraction of that brand new work we're doing is wasted work because I didn't know that you were going to end up throwing it out later just to extend a type unstable call like we talked about earlier. So I think more caching is great. It might cause some improvements, but I just don't think it's going to get us all the way there to solving this problem. And so then finally, I think the main option remaining is to try to improve this heuristic directly. We could try to add some smarts to the compiler, but I'm not quite sure what we'd want to do. So I think the main thing we might want to consider would be to give the compiler a hint. Right now, what it does basically is that it checks whether or not you have a certain number of matching methods, and if it's below that number, it can manually optimize and then say, add a little marker to say invalidate if this ever changes. But I think what we really want is something more like the ability to say, will this thing ever see new methods? And then we can jump straight to that dynamic call if we know that you're going to end up extending this interface. And I think this has been, I know that this has been brought up before in the ecosystem. Like, if we had interfaces like static languages do, then we wouldn't have this problem. And I think there's some truth to that, but I also think that there is some design space that we haven't explored yet, which is in particular that we don't need type information to make this do the quote-unquote correct thing here. Like, our dynamic call is already slow, and we're already happy with it after the invalidations. The problem is the invalidations that we have to pay in order to get us to the slow dynamic dispatch. And so we don't need type information. All we really need is a single bit of information, which is, are you going to be putting new methods here or not? And then if you have type information, that's great. Like, then I could use that to say, oh, you not only promised me that you're going to put new methods here, but any of the methods you put there are going to return string. That's even better. Now I can optimize this and give it a better ABI. I don't have to box the return type every time it comes back out, for an example. But that's not required to avoid the invalidation. That's just required to optimize the ABI when we call into it. So this is my idea about, I think, the direction we should potentially explore in. But more importantly, I think the big takeaway here is that if we're going to accept type unstable code, I think there's a fundamental issue about guessing whether or not we're going to see extension, like new methods in different parts of the method table. And when we get that guess wrong, we pay the cost in form of invalidations. And so the real question is, how can we start to guess that right? And that's it. That's my talk.
So first, actually, I don't remember. This is the last talk, I think, right? So I'm not going to be aggressive about cutting off questions this time. So did I see? Did you, Stefan? Okay, yeah.
Could we? It seems to me that the problem with invalidation here is that you then have to recompile all the code.
Yeah.
I mean, my immediate thought is, like, is there a way to patch the existing code? But I guess part of the problem there is that a lot of the type inference that you did is probably wrong at that point.
Yeah, we do lose a lot of type information. I think the main thing, yeah, I think there are some big design questions to figure out there. I'm a little bit skeptical that you could get that to solve all these kinds of issues, but it would certainly be nice to have an extra tool in the tool belt. The other thing that would be particularly nice is that one of the things that gets brought up in this space is that, for example, we can't really use interfaces because if we add an interface with a type assertion in base, then it wouldn't be backwards compatible. But if we had something, for example, like on-stack replacement where we could just drop down to an interpreter and leave the compiled path with the type assumptions in it, then that would be a huge improvement. And then you just have like an optionally enforced interface that gives a hint. Like, if you want your code to be compiled, compile with the interface. If you don't care about being compiled, then do whatever you want.
Well, I mean, yeah, I guess one version of that is that you compile the code assuming that there's a limited number of methods, but in such a way that it will work correctly if there are more methods. So then you sort of have the fast path code, but you also generate the slow path code at the same time. So then you don't actually have to invalidate because it'll still work. It's just slow.
Yeah, we can do that. I mean, the way you described it is easy. I think the hard part is to know which methods you want to include. And then when you're still giving up type information when you do that because of the else branch. And that's still a big
Well, one of the branches has bad type information and the other one has good type information.
Right,
I don't
but
know
then
if
they
that's
merge.
helpful,
And
yeah.
I just mean that it's still, like, you don't get the case where we talked about here, where we can world split, for example, in your internal code, and I get good type information with just string coming out of this. I don't get to recover that type stability anymore if I do that.
I think the worst thing about that is it makes it sensitive to the order in which you load packages and define methods, which ones get good performance and which ones get crappy performance. But, you know, we're in a space of playing trade-offs, so.
Yeah, I wanted to ask about exactly this example because, I mean, you don't have to use an abstract type, right? I mean, you could define struct type 1, type 2, and then do a const union abstract object of both of the types if you really wanted it to be final, and that would do away with the problem, because then it, like, okay, yeah, because I mean we had this long Slack thread yesterday, and I made my opinion there clear already. But I feel like if it was really disabled world splitting, then okay, yes, probably some code would run slower than it currently does. But I feel like it would not be hard to fix, and it would be very predictable to fix the places where it hurts you, I feel like. But
yeah.
I mean, it's hard without any numbers about any of this, right? Like probably it would be good to do some kind of measurements on real world packages. And but yeah, I don't know if that was not really a question, just an observation about this thing. That
No, I can comment on that.
Yeah.
This, first of all, you're right that this example is something you could pretty straightforwardly optimize. If this really is the whole, world of concerns that you have just right here, you could rewrite that as a union type. And then secondly, I do actually agree with you. I think that the world splitting optimization is something we should try to see, like, what are the exact costs of turning it off? Where in the ecosystem do we start to run into, bad trade-offs there? This is mostly here to say that, like, there's a good chance it won't get us all the way there, and that we are really benefiting from this if we'll get a few examples. And we expect users to kind of write code like this. And so it would be nice if we come up with another solution that doesn't end up paying off type stability and the quality type inference that we have today.
Hi. Like you brought out the convert example, and like for me, I guess I don't have a super clear mental model of invalidations yet, but like convert in base already has like a ton of methods, right? So if you're adding a method to convert in like some package, like are you going to invalidate anything? Like it feels like anything which is already a dynamic dispatch is going to stay a dynamic dispatch, and so it wouldn't have to be changed.
So it depends on the exact call site. Convert may not have been the greatest example. I haven't actually checked how many methods for convert to string specifically that we have in the system by default. I actually don't think we have very many conversions to string, which might make this invalidate. But you're totally correct that if it's a common conversion target, then you might already have enough methods in the system that we go straight to the dynamic dispatch case, and then we're already kind of doing the right thing. Yeah, it's going to depend on the particular type that you're converting to and those kind of details.
And how much type information you can successfully extract from the call site. So.
Absolutely, yeah.
Yep.
Would you talk about the viability of disabling world splitting for code gen, but keeping it for type inference, and then invalidating only if somebody defines a method which returns a different type?
I think I understand the proposal. I'm not sure I can give you an off-the-cuff answer about how I feel about it, but it's an interesting idea. We should talk about it more afterward.
Cool, thanks.
Yeah.
I was curious about the case where if you had a specific, like 4 or 5, which is more than you're kind of looking at number of types, and then after that, you want to go to dynamics dispatch, and where you could even be, enough about the types you have, you could order the types so that this is the 90% case or 50% case, and this is a 30% case. You want those to be dispatched by if else. Otherwise, you go into the dynamic dispatch. Would there be a possibility to have something where you could specify that? So it's kind of like just a union, but there's a possibility it has to go to dynamic dispatch.
Yeah, I see. You're asking whether we can optimize specific callees that we expect to be more frequent than others. Maybe the default implementation is like a hot target, yeah.
Some sort of @ sign, whatever, to tell the compiler.
Sure.
I really want this stuff because performance is what I'm looking for.
Yeah, I think that's a very reasonable thing to explore as an extension to something like trying to give an explicit source text hint of these kinds of interfaces to the compiler, where we expect this kind of extensibility and you want to provide it, like let it know that you got a hot callee that's going to be more frequent than others. I also feel that that probably goes in the bucket of like, these improve the performance beyond what we already get today. Because what it does is you get to that dynamic dispatch, and then now that dynamic dispatch performs better than it does right now, which would be great. I think those improvements are awesome, but they're not the invalidation problem. Yeah. Yeah, exactly. Yeah, I do think that would solve another pain point for users. Yeah, absolutely.
Okay, I have just been informed that despite this being the last talk, we do need to cut this off. I imagine some of our very helpful AV people actually need to go home at some point. So with apologies for extending your workday, let's again thank Cody, and thanks to you all as well. Have a wonderful evening.
Oh, and I have a...